Okay, let's talk about esters. So this is the third priority in the carboxylic acid derivative functionality. And the way we name esters, some people could argue that this is one of the harder ones to name, but now that we've talked about how to name carboxylates, you'll see that this is not that much different from naming those particular derivatives. So the way that it works out for an ester is that you have to name an alkyl, and this alkyl will be the one directly bound to the oxygen that only has single bonds on it. And after that, the rest of the molecule is to be named as a carboxylate. So this is not that much different than saying, you have a metal right here instead of hydrogen, you still name this as a carboxylate. You have an alkyl instead of hydrogen, you name this as a carboxylate, right? But you always start with the quote unquote cation. And right here, the alkyl group is the honorary cation. All right, so here's an example, right? If you look at the molecule, you have to realize that, yes, you have the CO double bond with another oxygen bound to it, but directly bound to that oxygen that is singly bonded on both sides is just an alkyl chain. So that qualifies as an ester. Now, as far as naming it, though, you have to recognize that it is this chain here on the left side, which is attached to the oxygen that is only singly bonded, that is to be named first. And because of the attachment, this is specifically known as sec-butyl, right? So also, the rest of the molecule is to be treated as the carboxylate unit, right? Everything else here on the right side, including that singly bonded oxygen. So we have sec-butyl on the left side, and the carboxylate that's on the right side is none other than benzoate, right? Derives from benzoic acid, eutropic acid, you add 8. So sec-butyl benzoate. That's basically the name of this ester. Okay, now another situation that could happen, right? It's one where you have a diester technically in the same molecule, right? And in this situation, you could be dealing with different alkyls attached to the singly bonded oxygens. Right now, in this example, they both happen to be the same, right? We have a methyl attached to the singly bonded oxygen. We have another methyl attached to the other singly bonded oxygen. So it's basically a dimethyl derivative. And if you look carefully at the rest of the molecule, that's basically the conjugate base of oxalic acid. So this ought to be oxalate. So the name itself would just be dimethyl oxalate. Okay. Another example, right, where I purposely changed the chain so they're different from each other. On the left side, we have an isopropyl substituent. On the right side, we have an ethyl substituent, right? And then in the middle, if we look carefully, this is a 2-methylene linker. We also know this as ethylene. This qualifies the molecule, and also it's aliphatic, right? So there's no double bonds in there. This qualifies the molecule as succinic acid, right? So as far as the name goes, ethyl goes prior to isopropyl, right? So it will be ethyl, isopropyl. And then since this is a succinic acid derivative, it's known as succinate, right? The conjugate base in essence. All right, so here we have another one. And what we recognize is that, yes, what's bound to the singly bonded oxygen on the left side, it's a phenyl substituent. On the right side, it looks like it's a phenyl substituent, but notice that we have a methylene linker in between the oxygen and the phenyl ring. So this whole thing together is benzyl. So we have a benzyl substituent, then we have a phenyl substituent, right, listed alphabetically. And then what's in the middle derives from fumaric acid. So this is fumarate as a conjugate base. Okay, and then one more just to kind of emphasize the full scope of everything. Okay, so here on the right side, we have an ester, right? On the left side, we have just a regular carboxylate, but we treat them the same way because they're all part of the same molecule. They're not different molecules. It's just a carboxylate component on the left side and an ester component on the right side. And if you think about it, right, here we're going to name the cation first, then the alkyl, then the carboxylates. just by consensus, right? Because cations always have to be listed first. But if you think about it, as far as the structure is concerned, the carboxylate and the ester unit are not trans, excuse me, para to each other. And what that means is that the middle section is deriving from terephthalate. Um, so we're going to first name lithium, then we name the alkyl chain, which is propyl, and I already gave it away, right? So this is terephthalate due to the para substitution. All right, so that's pretty much the idea with esters. So let's touch upon acid chlorides really quickly to complete, this video. So acid chlorides, we've talked a little bit about in the past, namely the fact that you can make them directly from carboxylic acids upon treatment with thionyl chloride. And then these things are very useful to do various types of chemistry, especially if you use mild reagents like lithium tritibitoxy aluminum hydride, or if you use lithium dialkyl cuprates. You could make aldehydes and ketones respectively from what used to be carboxylic acids, right? Now, what we didn't really talk about though is how you actually name this thing. So much like everything else, you start by naming a carboxylic acid, and once you do that, you drop the ic acid ending, and instead of that, you replace it with acyl halide. Now, the halide depends on the actual halogen that you're using. If it's chlorine, then you call it acyl chloride. If it's bromine, then you call it acyl bromide, etc., etc. So an example like this, right? You gotta realize that yes, it is an acyl halide altogether, specifically an acyl bromide. The longest chain is 1, 2, 3, 4 carbons long, and we have a methyl substituent at position 2. So altogether, this is known as 2-methyl butanoic acid if it were a carboxylic acid. But acknowledging that we don't have an OH right here, but rather a bromide, we drop the ic acid and we replace it with acyl bromide, right? So this will be known as 2-methyl butanoyl bromide. Okay, here comes another example. Same idea. We go for the longest chain that has the most amount of substituent. So that will be the chain going from literally from right to left. So that will be 1, 2, 3, 4, and 5 carbons long. So we're looking at a pentanoic acid derivative, right? And we have an ethyl, a second ethyl, and 1-methyl substituent. So 2 ethyls, 1 methyl. So this will be known as 2,3-diethyl, 4-methyl pentanoic acid to start off, right? And then we acknowledge that it's actually a chloro that we have here, not a hydroxyl. So we drop the ic acid and we go with acyl chloride. So this is now pentanoyl chloride. Okay, let's do one more. We have now a benzoic acid derivative, right? But this time around, we have an iodo instead of the hydroxyl that will make this a carboxylic acid. So we drop the ic acid and we name this acyl iodide, right? And then that will complete the series right there. So the last thing that you might encounter, which kind of goes hand in hand with the fact that carboxylic acids cannot be part of a ring system, they can only be attached to a ring, is that we're going to have to address that. So if we do have a situation like that where a ring system is present, then we name this thing like we would normally name the carboxylic acid, but then we're going to drop the silic acid portion of the name. So now we're dropping extra letters. And what we will do is we'll replace that with acyl halide. So, for instance, if you have the following ring system, right? This is cyclopentane. If it was a carboxylic acid, you would be saying cyclopentane carboxylic acid. But because it's a chloro group, we drop the silic acid, get it? And we replace it with acyl chloride. So in reality, what you're saying is cyclopentane carbonyl chloride, right? To be technical. Okay, now here's a more complicated example. It's a bicycloalkane. And we have the acyl fluoride this time around sticking out of the ring, right? So as far as determining the count, you can remember the bridgeheads have to be, one of them has to be position 1 by default. So you just pick the bridgehead so that you end up giving your functional group the lowest number possible, and also your substituents. And then the rules of bicycloalkanes in this case kind of like screw you over a little bit, because not only must the bridgehead be position one, but you first have to go through the longest ring. After that, you go through the second longest ring. So that means that even though we're choosing the bridgehead here on the very front, the acyl fluoride moiety cannot be position two, because that's not the longest chain in the ring, right? So we have to make all this, trip all the way back here to the second bridgehead. And because at that point, the rest of the two rings happen to be the same size, that's the reason why we can now choose to go towards the carbonyl fluoride. So as far as naming this thing, we would say, okay, positions 2 and 3, we have methyl, so 2,3-dimethyl, and this is a bicyclo, 3 carbons on the left, 1 carbon on top, 1 carbon on the right side, so bicyclo 3.1.1. Altogether, that's 7 carbons within the bicycloalkane structure. And we have the carboxylic acid at position 6, right? But now we acknowledge that it's not a carboxylic acid, but rather an acyl fluoride. So we drop silic acid and we replace it with neal fluoride. So carbonyl fluoride. All right. And then the last one to finish up the series, I'm bringing a spiral compound to kind of give you all those variations. And in this case, for the spiral compound, now what we have to remember is that position one is not the bridgehead, but rather the carbon adjacent to the bridgehead on the smallest ring. And then you work your way around the smallest ring back to the bridgeheads, and then you move in the opposite direction to complete the numbers for the longest ring in the chain. So here it happens to be totally cool that position one is in fact where the carboxylic acid moiety is presented. So this will be known as spiro, 2 carbons on the smallest ring from the point of view of the bridgehead, and 5 carbons on the left side from the point of view of the bridgehead, right? So spiro 2.5, altogether octane, 1 carboxylic acid. But now we acknowledge that it's not a carboxylic acid, so we drop the silic acid and we replace it with neal iodide. So spiro 2.5 octane, 1 carbonyl iodide. And then the last thing I just want to mention in respect to this is that I want you to notice the difference with spiro and bicycloalkanes. Bicycloalkanes always descend numerically as far as counting how many carbons you have to the left, to the right, to the top of the bridgeheads. But for spiro compounds, you actually go in increasing number. So it's kind of annoying because you're kind of doing the opposite thing. But hopefully that will not get you tripped up on the on your homeworks and exams. All right, so that concludes the ester and acid chloride nomenclature. In the next video, I'm going to tell you about how to name amides and nitriles. So see you then.